All right, in this video, we're going to go into specific examples that are used for optimization problems that deal with business and science. The science kind we've already talked about before, but the business ones we haven't spent as much time on, so I wanted to clarify a few terms before we jump in. So revenue is describing how much money X number of items brings in. So before we consider, of course, what you see below, before we consider any cost, just how much money it's bringing in. And we often use a capital R to represent it, R of X. And the way you can calculate it is often it's the number of items times price. Sometimes they give you the price, but sometimes the price is kind of like a formula or expression that you're going to use instead. Now, of course, cost is something we have to deal with. And this is not really the best definition because I'm just going to say how much it costs to make X items. So not so much a definition as just like explaining how these things are related. And of course, we often subtract cost from revenue when doing calculations for profit. And we'll use a capital C for cost. So then profit is the end game here. So after we take into account revenue and cost, it's how much money you actually end up with. Okay, and there's a couple ways we can express this. So we'll use P for profit. And what we're going to be looking for in a problem is usually to make maximum profit, unless, of course, we're like trying to sabotage someone. And where maximum profit would occur is going to be where P prime of X equals 0, right? Because P is our profit, so that's the function we're going to work with in the problems. And it's very similar to other optimization problems where the first derivative is telling us where those max and min occur. Of course, we'll still use a sign chart to show that it's a profit. We can also express this as, since profit is a combination of revenue minus cost, we can think of it that way. So R prime of X minus C prime of X, where that equals 0. Because again, I guess I could have added this up here. Profit is equal to, let's do that, is equal to revenue minus cost. I think I said it, but writing it is always better. So if this is how we calculate profit, we can simply find the derivative of each function separately, and that difference is the same. And because of that relationship, we could also simply add cost over, the derivative of cost over, and it would be occurring where this is also the case. Now, I don't really use these other two forms very frequently. To be quite honest, you usually will only find the equation of profit first and then derive that, but it's something to be aware of if the need ever arises. All right, and then the science applications, like I said, we've talked about these before, but it's been a while. So the one concept that a lot of students get confused with is distance versus displacement. So let's go over that real quick as well. So distance is the total amount traveled. Like from beginning to end. And so a lot of times we think of this as kind of like an odometer. Like if you have a Fitbit or a smartwatch that counts the number of steps you take throughout the day, the direction is not going to take away any steps. Like you're just measuring how far you've gone through the whole journey, not necessarily just from the distance where you started to where you ended, because that is what displacement is. Okay, so how far you get from the starting point is displacement. right? And I would say that displacement is very easy to calculate. It's just n minus start, in position minus start position. That tells you the distance between them. For distance of the whole journey, we have to instead take into account any change in direction as well. So we have to use velocity, which is the first derivative, velocity intervals to figure this one out. So it's a little bit more involved. All right, so let's do our first example here. It's going to be a revenue cost one. So it says a manufacturer can sell X items a week for a revenue expressed here in this equation. And that's in cents, which is something to watch out for at the end. And it costs this amount, cents, again, make sure those match, to make X items. Is there a most profitable number of items to make each week? If so, find what it is. So the first thing we're going to do is write a profit equation by combining revenue minus cost. Okay, so our revenue formula is 200x minus 0.01x squared. And then we're subtracting with parentheses, because this is where you'll make a mistake if you're not careful, the cost expression, 50x plus 20,000. And now we'll distribute our subtraction sign all the way through. And then what like terms do we have? We have 200x minus 50x that we can combine. Oh, whoops. I'm going to pull the x squared to the front because we see that this is turning into a quadratic. And then if I combine 200 minus 50, that gives me 150x. And then that minus 20,000. All right, so at this point, you have a couple of choices. First, we have to take the derivative, I guess, before we make those choices. So let's do that. So that's going to be 2 times negative 0.01, which just gives us negative 0.02x plus 150. And then we're going to set that equal to 0 to find where a potential maximum may occur at a critical number. And this one we can actually just solve by hand. That's not so bad. Never mind. No choice to be made. So we're going to do that. And when we divide by decimal, it should get really big. And in fact, it gives us 7,500. Now, we still need to verify that this is a max. So we would make our little sign chart here at 7,500 for P prime versus P to figure out what's going on here. So if I choose something that is less than 7,500, then it's going to be less than 150, that's negative, so when I add, it's still going to be positive here. But if I choose something much, much bigger and I add 150, it's still not going to be enough to make it positive. So we're going to get increase, then decrease, which means that 7,500 is a maximum. So, you know my favorite statement. I'm going to try to squish it down here. Thus, not P, oops, X equals 7,500 is a max since P prime changes positive to negative. So this is the calculus explanation. Oops. The sign chart alone will not be counted in a free response question, but you need to do it so that you can write this statement with an explanation that will count. And now we can actually answer the question. So is there a most profitable number of items? And the answer is yes. And then just for fun, let's find that profit so that I can make sure we would do that correctly. So you could plug it back in to that equation there and find P of 7,500. And it should give you a pretty large number, 542,500. And the reason I wanted to actually find this is because this is the type of problem you have to be careful, because our original problem was in terms of cents. So like had they asked you for the maximum profit, you would need to be very careful with this number and make sure you use the correct units in your answer. So let's craft our answer here. So the most profitable number of items to make each week is 7,500 items. And this yields a maximum profit. And then if this was in cents, we would simply divide by 100 to get it in dollars. So that would be what, $5,425, right? To get a maximum profit of $5,425. All right. So this is our first example from beginning to end. Okay, so let's take a look at our next example. It says, given that the revenue is represented as 10x and the cost is represented as x cubed minus 6x squared plus 15x plus 5, where x represents thousands of units. Again, watch out for stuff like that when you write your final answer. Is there a production level that maximizes profit? Blah, blah, blah. Okay, so let's go ahead and write our profit equation. So revenue is 10x minus cost in parentheses, which is x cubed minus 6x squared plus 15x plus 5. All right, we're going to clean this up. Minus x cubed plus 6x squared minus 15x minus 5. And then I think we have one thing we can combine here. 10x minus 15x. So I'm going to pull the negative x cubed out front, then plus 6x squared, and then 10 minus 15 becomes negative 5x, and then a minus 5. So there's our profit equation. We find that first derivative to look for the critical point, so that becomes negative 3x squared plus 12x minus 5. Set it equal to 0. Oh, you see where we're going with this, right? Well, let me give you a hint. Obviously, we would want to try factoring. That's what we always do. This one actually doesn't factor. So if you have a calculator, there's lots of ways you can go about finding this graphically. But don't forget that the quadratic formula is also helpful in these cases. So let's try to remember that just in case we ever need it. So opposite b plus or minus square root b squared. Let's see, that would be what? 12 squared minus 4 times a times c all over 2a. All right. And that's going to become, let's see, if I simplify 144 minus 60, so what, 84? Oh, I guess I need a plus or minus there. And then 84 in here, and then negative 6. We should be really good at estimating square roots with that linearization skill we've picked up, but I won't make you do that. So basically we're going to have two possibilities here to check this time. So if we add the square root of 84, we'll end up with 3.528, and if we subtract it, we get a smaller decimal at 0.472. So this is one where the number line is especially important because we have two possible answers. So let's go ahead and take a look at that here. Well, let's do a little bit further. So we have 0.472 to check on, and we have 3.528 to check on. And this is for p prime to see what's going on with p. All right, and this is one where I would probably use a calculator to help me out since we didn't factor it, but we could also just try to use easy test points. So something to the left of this one would be 0. And if you plug that in here, you can see you're going to get a negative. So, doop. And then something easy between here, any whole number, 1 probably is the easiest. So we'd get a negative 3 plus 12 minus 5. That's enough to make it positive. And then something larger, I don't know, 4, 5, a lot. But it seems like if we have a really large number that we're squaring and multiplying by negative, this won't be enough to change it to a positive. So I think we're going to go ahead and say this is definitely going to end up being negative because of that negative 3 coefficient. So here we have to make sure we're paying attention to the type of problem we're working with, which is to maximize profit. And so in order to do that, we would want to use this particular situation and not the 0.472, like I said, unless you're trying to sabotage someone, which is not the scenario we're going to think about right now. So we're going to say thus x, I guess, estimates to 3.528 is a max since p prime changes positive to negative. And then I'm going to write our final answer up above for the sake of room. So we're going to say the production level that will maximize profit is approximately and then there's a couple different ways to do this. I would just leave it in the unit that we found in the calculator, so 3.528, but remember that it's in thousands, so obviously 3 units is not what we're trying to say here, so that many thousand. So yes, you could go ahead and convert it, but I just like to do things as simply as possible, so I'm just going to include the 1,000 units as part of the answer. And that concludes question 2. So now question 3 is kind of a review problem with the velocity and acceleration, things that we've done before, but it's been quite a while. So it says a particle moves according to this function here, and remember S of t is the common notation used for position, where t is in seconds and s is in feet. So what is the velocity after 3 seconds? So velocity is the first derivative, so v of t is going to equal the first derivative of our position function, which looks like we would get, let's see, 3t squared minus 18t plus 15. So that first derivative is velocity, or how the position is changing, and then we're actually going to find it at 3 seconds by plugging in a 3. And this gives us v of 3 equals negative 12. And then make sure to include units when you're dealing with particle motion problems. So velocity is feet per second, and acceleration is feet per second squared. All right, so when is the particle at rest? So for this, we're looking for when the velocity is 0. When the particle is at rest is when it's not moving. So we're going to take that derivative we just found in the previous problem and set it equal to 0. And this is one where factoring should work out for you pretty well, because we can factor 3 out. So what is that? Minus 6t plus 5. And then we can write that as 3 times t, minus 5 minus 1, I guess is our only option here. Alright, so we're going to be checking, or I guess it's going to be at rest when t equals 1 and t equals 5 seconds. Those are the times when the velocity is 0, which means that the particle is at rest. The next question says, when is the particle moving in a positive direction? So this is still dealing with velocity. So here we're looking for when velocity is positive or greater than 0. So for that, we're going to use our critical numbers from the previous question and make a sign chart. So we have 1 and we have 5. And I'm kind of just using this right above as a place to plug in test numbers. If we plug in something less than 1, we're definitely going to get a negative times a negative, which means it ends up being positive. And then if I pick, let's see, like 2 minus 1 is positive, but 2 minus 5 is negative. And then if I pick in a really big number, obviously positive. And I kind of get to ignore this 3 because it's positive. If we had factored out a GCF that was negative, however, you would need to include that in each region, because that would definitely change what's going on. So we have positive, negative, positive, although I guess we can just see from the signs themselves that the positive motion is occurring for times from, we're going to assume time starts at 0 probably. So from 0 to 1 and then any time after 5 seconds. So the particle is moving in a positive direction from 0 to 1 seconds and after 5 seconds. There we go. And last but not least, find the total distance traveled. So this was the harder of the two because we're going to have to see the directional changes. So again, we're going to use our previous information that the velocity is 0 or the particle's at rest at 1 and 5. And we're going to use our start and end points. So this particular one says in the first 8 seconds. So that means we're going to have to find the position at 0 and the position at 8. If all we were doing is finding displacement, that's all we would need to do. But since we're looking also for the total distance traveled, not just the distance between the start and end, we have to look at any other time the particle changed direction, which occurs or potentially occurs when the particle is at rest. So we also have to look at 1 and 5. So if we do this real quick, we're going to get, so we're going to S. S was the original function. So you would be plugging those values into this particular equation. So S of 0 is pretty easy. That's just 10. And then S of 1, let's see, would be 1 minus 9 plus 15 plus 10. And that's going to give us 17. And then I went ahead and figured out the last two because they're a little bit more involved, but we should get negative 15 and 66. Okay. So then I need to figure out, so these are the locations of the particle. Like if it were on a number line, this is where it would be sitting at. So it starts at a 10 and then it goes to a 17 before it stops. So the amount of change occurring there is 7. Then it's all the way at 17 and it goes to the left until it reaches a negative 15 position. So that's a lot of change. That's in fact a change of 32 from 17 to negative 15. And then it changes direction again and goes back all the way from negative 15 to the right to positive 66. So that again is a very large change, which means it went a distance of 81. And we simply add up all those distances and we'll get 7 plus 2 plus 1 is 10, carry the 1, so 120. Okay, so the distance traveled in the first 8 seconds is 120 feet. Had I asked for the displacement, again, all I would have had to do is take S of 8 and subtract S of 0. So the displacement would have simply been 56 feet. And that's a lot easier to find. The distance traveled, we have to look at all those position directional changes as well. But this concludes our video on business and science applications with optimization.